So Peter is an associate professor in the cryptography and security group at Boston University. And he has worked extensively on bringing the theory of secure multi-party computation into practice with more efficient protocols and implementation. Additionally, he works on various related technologies such as zero-knowledge proofs, threshold cryptography, homomorphic secret sharing, and post-quantum cryptography. He has also been involved in the design of a FIST signature submission to the list for additional post-quantum signature.
Thank you all for the nice welcome. And thanks, Carsten, for giving a nice introduction to MPC-in-the-Head, which I think should nicely set the stage for some of the things I'm going to be talking about here. So what I'm going to actually mostly be talking about is something that looks like a very different way of building zero-knowledge proofs, which I call the VOLE family. And in the first part of this talk in this session, I will introduce this tool called VOLE, Vector Oblivious Linear Evaluation, and show how this can be used to build what I think of as very simple, mostly information theoretic proof systems, which are kind of nice and easy to understand, so good from an educational perspective, but also turn out to be very efficient in many contexts. They are unfortunately limited in this case to the designated verifier setting. That's where we have a prover who has some secret randomness, and we can't make that randomness public, so it's inherently just a two-party protocol. And for instance, can't be made completely non-interactive. But then in the second part of this talk, in the next lecture, we'll show how we can actually transform these proofs and obtain publicly verifiable proofs. And this is where the kind of techniques we'll use will also draw inspiration from MPC-in-the-Head and things that Carsten's been talking about, and we'll perhaps see a bit of a connection here. And all of these works are kind of a pretty recent line of work over the last 3-4 years. As I said, I think many of the techniques are kind of very simple and information theoretic, but there's also a lot of optimizations and other things that can be thrown at it. Okay, so where does the VOLE family of proof systems fit in the whole scope of zero-knowledge proofs that you might have come across before? So on the one hand, we have these kind of nice succinct proof systems like Ligero and Starks and Growth 16 and many other kind of things in between, where typically across these proof systems, you get a kind of trade-off between the runtime of the prover and the proof size. So if you want, the super succinct proofs with very small verification, then you're going to pay more on the prover side to get that. And at the other end of the scale, we have things like MPC-in-the-Head, where the proof size is linear, but the prover, on the other hand, is much, much faster. And then we have these VOLE-ZK proof systems I'm talking about, which I think of as a kind of optimized version of MPC-in-the-Head. So they sit maybe similarly in terms of proving time, but a little bit smaller in terms of proof size. And in fact, sometimes you can even get them slightly sublinear in the circuit size for what you want to prove. Okay, and concretely, we can actually get kind of very nice communication costs in terms of the circuit size. So yeah, roughly 1 field element per multiplication gate or AND gate in a Boolean circuit, or even a little bit better. And of course, this comes with this possible limitation of the designated verifier setting, but we can sometimes work around this. Yeah.
Can you just explain this designated verifier again? I'm not sure if I fully understood what the difference is.
Right, so it's where the verifier has some secret randomness, which it uses to generate its messages, so it can't just reveal this to the prover.
Public coin.
It's not public coin, exactly. You can't apply fiat-Schmidt. Okay, so how do these proofs in the designated verifier setting work? So first off, I need to introduce vector oblivious linear evaluation, which is an ideal functionality between two parties, Alice and Bob. In my slides, Alice will always be the prover and Bob the verifier. And Alice has an input, which is a set of vectors, a vector of lines, which you can think of as two vectors of field elements, where each pair of field elements can be seen as defining a single line of the finite field. And Bob has an input, some scalar in the field, delta, and wants to learn at the end of this ideal functionality the result of evaluating at his point delta all of Alice's lines. Okay, so vector oblivious evaluation. Oblivious because of course we want the vectors to remain secret from Bob and Bob's point delta to remain secret from Alice. Okay, so in this case, you can see that Alice potentially has complete choice over her vectors V and W. But today the V portion of Alice's input is actually always going to be uniformly random, while W will potentially be chosen by Alice. In some cases, you might just look at a version where both of Alice's inputs are uniformly random, called random VOLE. And this is also fine. If you have that, it's very easy to realize this one where W is chosen just by sending a small correction value from Alice to VOLE. Okay, so this we're just going to treat as a black box, so some magic box in the sky, which you can think of as a special setup assumption done once at the start of the protocol, and then we'll use this to help get the zero-knowledge proof.
Sorry, could you please elaborate again on the illustration on the left side? What was the
Sorry.
what's the red boxes on the left side?
Right, so the red is Bob's input, so that's the delta, and then we get the evaluations, which are the points on the other side.
Ah, okay, this is the evaluation vertical line.
Yeah.
All right, I see.
Yeah.
Okay.
Okay, so I think for the interest of time, I'll just skip over this and say a little bit about some kind of known techniques for realizing this box. So vector OLE, I guess, originally is a kind of classic tool used in secure two-party and multi-party computation protocols. You can build it with linearly homomorphic encryption. There are also more recent constructions using a tool called pseudo-random correlation generators based on often the learning parity with noise assumption, which have very nice communication complexity. So it can even be sublinear in the length of the vectors when you just want to obtain random voles. And the last version I want to talk about is based on oblivious transfer extension techniques, which also come from secure computation. And this is actually very related to the VOLE-in-the-Head technique, which I'll be talking about in the next lecture. This only uses symmetric primitives, it's very fast, and also has pretty good communication costs. Okay, but for now we treat it as a black box. And first off, let's say, what's the most basic thing we can do with a VOLE? So we can build a nice information theoretic commitment scheme. Okay, so we just take each element from the VOLE output, or each pair of elements for Alice, and we'll view the W as Alice's input, which she wants to commit to. And then the kind of commitment information that Bob learns is just his Q output, the evaluation at the point delta. Okay, so this is a commitment to W. If we want to open this, then Alice can just send the line over to Bob, who will check the line equation holds. And okay, just let's think a second about why this is a binding commitment scheme. So supposing Alice is going to try to cheat in the opening phase and send maybe a different line. So here we've got the original line P of X, and then another line P prime of X. So of course, for Bob's check to actually succeed, Alice will have to come up with a line that intersects with the original one at the same point delta. And if we work over a sufficiently large finite field, then there'll just be a 1 over field size probability of this happening. So we get statistically binding commitments. Okay. Of course, a commitment we also want to be hiding, which in this case we get just from the fact that the V value that Alice chooses is always uniformly random. So Bob learns nothing about W from just observing Q. Okay, yeah.
Since we can't have, I guess, both statistical hiding and binding, I guess the trick here is that the VOLE will use some computational.
Exactly, yes. So this is
We assume the VOLE is a black box, this ideal functionality then.
where the setup functionality.
Yes, there's also secret value, the delta, right? So
Yeah, so delta is secret. Yeah.
that's kind of the same value that will be the
Yes.
secret in the designated variable.
Yes, so delta will always be fixed.
So I can ask a stupid question. Why does it look like Schnorr reversed? Is there any connection at all, or is it just like I'm hallucinating?
I think there's no significant connection. Maybe coincidence.
I'll investigate it later.
Yes, Schnorr is also linear.
Yeah, but it's like literally you just revert the parties. I mean, it's like really weird.
Okay, so one nice thing about these commitments is they're linearly homomorphic. So since for each commitment, say if Alice commits to multiple things, Bob will choose the same, though this fixed value of delta, that's the evaluation of, which means if we have, say, two lines committing to points Wi and Wj, we can add them together and we get a third line, which is just the sum of the original two, and Bob can add together his evaluations to learn the sum of the kind of sum and commitment values. Okay, so we can apply any linear operation over the finite field on commitments. Okay, so what can we do with this? Well, thankfully, way back in the 1990s, Kramer and Damgaard showed how if you have linearly homomorphic commitments, you can actually use this to get zero knowledge proofs. And they proposed a kind of somewhat general blueprint, which I'll roughly follow at least in the beginning, and show you how you do this here to prove knowledge of a satisfying assignment to an arithmetic circuit. Okay, so Alice has proven that she knows some x such that evaluating the circuit on x gives some known output. And we follow this commit improve approach where Alice will start off by just committing to all of her inputs to the circuit. So I put these in locked boxes here. And then we'll commit to what I call the extended witness, which contains not only the input, but also the outputs of every multiplication gate in the circuit. And we'll use these to kind of help ensure that the circuit evaluation is correct as we go on. So now we want to fill in the rest of the wire values in this circuit with commitments. So we can rely on the linear homomorphism of the commitment scheme to evaluate the addition gates and obtain these committed values here. And now, of course, we're guaranteed that the linear operations will work correctly thanks to linear homomorphism. So the only thing we need to do to be sure that Z is correct is prove that the multiplication gates were committed correctly by Alice. Okay, so if you have some way of verifying multiplications of three committed values, then we can do the whole proof for circuit satisfiability. Okay, so how can we do multiplication gates if we have voles? Well, one thing that's actually really nice is because these commitments are lines, we can view them as polynomials. We can't just add polynomials, we can also multiply polynomials. Okay, now, of course, we multiply two polynomials, Alice gets this quadratic polynomial. And if we look at this, if the original lines were commitments to Wi and Wj, now the quadratic polynomial has Wi times Wj in the degree 2 coefficient. Okay, so we can still view this as a commitment to the product. One catch is that now the degree has increased. We're working over a finite field, so we have potentially two roots of this polynomial, which means when you look at the binding argument we saw previously, now you get soundness error 2 divided by the field size instead of 1. And of course, we also get more storage and communication costs for opening these things. So we can't do this indefinitely, but it does help. Okay, so let's look at how we actually rely on this homomorphism to prove some multiplication relation among three committed values. Let's say we have Wi, Wj, and Wk committed. So we can locally compute this degree 2 commitment for the product, Wi, Wj. And now we just want to prove this contains the same thing as the Wk commitment, okay? So if we take the line from the Wa commitment, let's call this Pk of x, and we multiply this by x and then subtract it from the degree 2 polynomial, then we should get these things canceling out, right? If Wk is Wi times Wj, we should get some degree 1 polynomial. Okay, so Alice will just send over the coefficients of this degree 1 polynomial, and Bob will check the equation of this. One catch here is that before sending over these coefficients, we have to mask this with an additional random commitment or random degree 1 polynomial to make sure that we preserve the zero knowledge property.
Excuse me, what's PK?
Right, so PK is the commitment to the Wk, it's the output of the multiplication gate. So I'm writing this as the polynomial representing the line. Yep. This is all polynomials in X.
Just wondering if you can get into any trouble if one of the lines is the zero polynomial, but I'm not sure if this matters if one of those lines would be
It doesn't matter.
El problema es constant.
Yeah, I was just thinking about using the number of roots, if you need that for the binding.
You only care about it being non-zero if there's any kind of inconsistency. So if WK is not equal to the correct product, then you'll get a non-zero degree 2 polynomial. If it's all zero, then you know it's correct, so it doesn't matter what the rest of it is.
Also, if you open the, if you commit to like essentially the all zero polynomial, degree 1 polynomial, and you want to cheat and open it to something else, well, the something else can only have one root, because otherwise it could be this polynomial. And so again, you have a chance 1 over field size to cheat only. So same.
Okay, so just to recap a little bit, I'll show how this whole protocol works on one slide. So we start with this vol setup, where now we're going to have vectors of length n equals to m, where n is the number of inputs to the circuit, m is the number of multiplication gates. And we have these m extra masks for each multiplication check. And then Alice just sends over these masks degree 1 polynomials for each multiplication gate. Bob checks them. And we have soundness error 2 divided by the field size. And the cost is just sending 2 times m field elements plus this vol setup. Okay, so this is like super simple, non-interactive after the vol setup. This comes from the line point zero knowledge protocol. I did Maisha and Ostrovsky from 2021. So there's a few things we can do to improve this. One is to try to do a bit better than sending over this polynomial for every multiplication gate. We can actually batch these together. So let's get rid of this and now change the setup so that we only have 1 extra random masking polynomial instead of m. And we can do this classic trick where Bob sends a random challenge from the field. And now instead of sending over all of the zi's, we take this linear combination by kind of viewing the zi's as coefficients of a high degree polynomial evaluated at a random point r. So we just need a single mask to make sure that this preserves zero knowledge. And now we're only sending over, 1 check value instead of 1 for every multiplication gate. Now the only cost of the dominant cost of this is just doing this vol setup of length roughly the input size plus the number of multiplication gates in this pre-processing stage. But we slightly worsened the soundness error because we have this potentially degree m polynomial here, where m is the number of multiplication gates, so we get this extra m over the field size term. Okay. Any questions so far? Good. I promise this will be very simple. Hopefully, this is living up to it so far. So
Could you go back to how ZI is used? So this is the thing that is like if you
how it was defined.
yeah how it's defined.
Yeah. So
Yeah, saying that
with this polynomial here.
Yeah.
So it's a degree 2 polynomial, but it should be degree 1 if things are correct.
This is easy to see because I must admit I don't see why if everything is correct, this should be a degree 1 polynomial. I mean this, yes, but why it's not the case that this might.
Right.
Why this implies like that I have only cheating probability.
Right. Okay. So I kind of brushed over that, I guess. So, okay, if the multiplication is incorrect, this is a degree 2 polynomial. Yeah. So if Wi, Wj is not equal to Wk, we have some non-zero value in the degree 2 coefficient of this polynomial. Okay. But when you send over the check values, you're just sending a degree 1 polynomial. So the check will basically only pass if this difference of what you send and what the actual degree 2 polynomial is happens to be 0 when evaluated at random point. So you have a non-zero degree 2 polynomial, which has to be 0.
and how does it depend on the witness? That you said you have to mask it. Like how would it?
So there might be something in like the lower order coefficients that depends on the witness from when you multiply the polynomials. So it's like in this degree 2 polynomial, the degree 1 coefficient, it somehow depends on the witness as well.
So again, just Just to recap, so the prover on the next slide sends all of the polynomials that we see, and also additionally these extra z's after. That I used
So it
for-
just sends all of these z's,
Right.
so one for each multiplication gate,
One first multiplication.
with-
Okay.
plus the masking value.
So the TCO and T1, they depend on the witness.
Exactly, the T0 T1. Yeah. So this one you just send the z's.
Right, but V and W define the original polynomials. That's what I was trying to say.
Right, so the z's are defined using the v and the
And
w.
V and
by
W are the
multiplying
original
them.
polynomial. These are the original polynomial that represent your computational trace.
Yeah.
It's just an extra for multiplications.
They only send something for multiplication checks.
The verifier, what will he know now? He will know the ZIs, the.
So he can compute the zi's evaluated delta,
Oh.
right, or what the correct version should be, based on its Q's.
Yes.
Yeah, and then it will just check that this is consistent with zi. It's actually sent.
So he will just check this in a single point then.
Yeah. Yeah.
How does he know the degree one then?
Right, you only send two coefficients. If the prover
Okay,
sends
okay,
more,
I
then
got it, I got it, okay, okay, okay.
okay. Good. So this is kind of the basis for everything moving forward. So it's nice to have some questions. So the next kind of possible optimization we can do is that, so remember we saw that these commitments we're using are kind of fully homomorphic, right? We can multiply more than once if we want, but then it'll just end up getting higher degree. So maybe we can try to take advantage of this and reduce communication slightly. Instead of having one commitment for every multiplication gate, we can do a bit better. Okay, so how does this work? So basically what we need is, instead of just doing the multiplication check, we have some more general degree reduction gadget. Right, so let's suppose we have some degree D polynomial, P of X, known to the prover, where Bob has some evaluation of this at a random point. And then we create a fresh commitment to the W value, which is encoded in the highest coefficient. This is now another degree 1 commitment. And we just want to prove that these things are consistent. So we can just do the same thing. We take the degree D polynomial, subtract x to the D minus 1 times the fresh commitment, and check that this is a degree D minus 1 polynomial that commits to, well, 0 when the degree D coefficient. So how do we take advantage of this and use it in the circuit evaluation? There's kind of a few different ways you can do it, which might depend on the exact circuit you're proving, but one kind of simple approach is just to do a lazy degree reduction. So instead of committing to all the multiplication outputs up front, we just commit to the inputs. And then we can go through the circuit, evaluate the linear gates locally, and also evaluate the multiplication gates locally until the degree reaches some limit. So let's say after 2 multiplications, we get to a degree 3 commitments. We can still add these degree 3 commitments to degree 1 and get another degree 3 polynomial, but maybe we say degree 3 is, our limit, and now we want to do this degree reduction to go back to 1, where then Alice has to send another commitment and communicate to make this happen. Now you get this kind of flexible trade-off where you can choose the degree based on how much communication money you save and how much extra computation you want to pay for to make that work out. So if you look at the communication complexity of this, then for each degree reduction, you're paying this 1 extra vol commitment to commit to the fresh value of the witness. And you're also doing this math check. Remember, these can all be batched together, so we can kind of ignore that. And if we look at a circuit which has m multiplication gates with maximum degree D, then essentially every log D multiplications, we might have to reduce the degree. So overall, we get m divided by log D commitments we have to make, or communication complexity around m over log D field elements, plus some extra D at the end for the batch check. So if you set D sufficiently large, you can actually get a roughly no log of circuit size saving in the communication complexity here, and get something that's slightly sublinear in the circuit size. So when you do that, then your computation will flow.
And you still need to commit to the witness.
Yeah, you don't need to commit to the input. Yeah, okay, so I think I will skip over some of this, except with a quick remark that, yeah, this stuff is actually pretty flexible. You don't always need to work over a big field. You can do small subfields of extension fields. There are tricks to mix and match computations over different rings or fields. And performance is also quite fast, around 10 million gates a second on a local implementation over a fast network. So I think overall, VOLE-ZK offers a kind of nice, simple information theoretic approach to building zero knowledge with this vector OLE setup. Flexible choices of parameters and fields or rings you want to work in, as well as this low proving time and also low memory costs for the prover, where since you do things right, the memory cost can be roughly proportional to that of evaluating the circuit in the clear. Of course, the downsides you get are that this proof size is still linear, or maybe slightly better than linear. And we're in this designated verify setting so far. Okay.
What's the cost of the verifier?
Similar to the prover. So yeah,